Alright, so hello everyone and welcome to another science video lesson. And in this video lesson, we will going to talk about module number 3. And what is this module number 3 all about? And that is the three types of plate boundaries. So last time we talked about what is the lithosphere and the layers of the earth. And on the second module, we talked about the earthquake epicenter. So how to find it and how to read the seismograph readings. Now for today, we will discover what are these three plate boundaries and where can we what in what place here on earth where we can find those plate boundaries, and what does each boundary differ from one another. So okay, come and join me and let's discover what are these plate boundaries all about. All right, so the plate tectonics. All right, plate boundaries are under the idea of the plate tectonics. All right, so plate tectonics is a theory that states that the outer mechanical layer of the Earth, which is called the lithosphere, is constantly moving. All right, so the lithosphere. Right, so as we all know that the lithosphere is made up of crust and the upper part of the mantle, which is constantly moving about a centimeter a year, right? So that is the plate tectonics. Now, if you reverse these two words, we have the tectonic plate. The tectonic plate is a huge chunk of rock, all right, which is the lithosphere, which is constantly moving. All right, so that is the tectonic plate. So as we all know, that the Earth is divided into several plates as what scientists have designated or assigned with. All right, so there are intermediate and there are major plates. All right, so on these plates that divides the Earth, okay, there are what they call these plate boundaries. Right, there are plate boundaries, which is it is a boundary between one plate and another plate. So what are these three plate boundaries that we are talking about? So the three plate boundaries that we are talking about is the first one, which is called the divergent, and the second one, which is called the convergent, and the third one, which is called the transform plate boundaries. Alright, so as you can see here on this picture, you can see the differences in terms of their movement. So the divergent is moving away from each other, and the convergent is moving, the two plates are moving towards each other, and the transform plate is, the two plates are sliding past each other. Alright, so okay, beyond this movement, there are several details that we will going to talk about this morning, and we will going to use some simulations in order for you to understand the movements done by these three types of plate boundary that we have right here. Okay, to start with, let's start first with the divergent plate boundaries, or we called it the constructive margins. Why we called it the constructive margin? Right, so at the middle of this plate boundary, there is what they called a ridge. All right, this is the ridge where new materials come, where new materials comes up from the mantle. Right, so when this new material comes up, goes up from the mantle, all right, what happens to this ridge over here? It is somehow spreading away from each other. All right, it is moving away from each other, thus pushing the plate to this direction, to the right. All right, and pushing the plate on this direction, I mean to the left, and pushing the plate on this direction to the right. All right. As it do so, new material is being dumped on this part at the middle of this plate that you have right here. Right. So new part of the in this part of the plate that you have, in this part of the boundary that you have right there. All right. So as the new material is being dumped here, it is pushed, okay, away from each other, and the materials that you have over here is somehow older than the one that you have at the middle. All right. So in terms of age, in terms of the age of rocks, the materials from the middle is somehow younger than the one over here at the side of this divergent boundary that you have right there. All right. So we called it okay, we call this part as spreading ridges. All right. So as the plates move apart, new material is being erupted to fill the gap at the middle. All right. So as it fills the gap at the middle, it pushes away the plate towards the side. All right. So that is the divergent boundary or the constructive margin. Now, okay, so most of the divergent boundaries are seen underwater. All right, so as our previous discussion talked about, okay, so it was discovered that the seafloor is made up of several rift valleys. Alright, so especially the one that is located at the Atlantic Ocean, underneath the Atlantic Ocean, which is called the Mid-Atlantic Ridge. Alright, so this particular place here on Earth, which is called the Mid-Atlantic Ridge, is an example of your divergent boundary. Alright, so why is it constructive margin? It's because the new material fills in the gap as it erupts from the mantle, alright, down to the Earth's surface. Alright, so up on the Earth's surface. So it constructs or it provides new material from to the Earth's surface. So okay, so as you go here, so we have here an example of how a typical rift valley is formed. Alright, so we have here the continental crust, and there is a weakened part of the continental crust where the mantle materials came out. Okay, so as time passes by, this mantle material is being erupted upward and replaces the one that is on the surface. And as it does, it pushes this particular part of the lithosphere to the side. Alright, so moving away, this part of the lithosphere that you have right here is moving away from each other. So the one at the middle is the new material that I am talking about that is coming from the mantle. Alright, so next, as time passes by, the gap between these two, okay, the gap between the ridge is getting wider, right? So as time passes by, and this is where okay, in this example, we have here a water that comes from an open sea that rushes towards this gap that is created by this spreading ridge that we have right here. Then, as it does, it widens and it widens over the past million years, and this is how the Atlantic Ocean was born. All right, so on the bottom of the Atlantic Ocean, there is a rift valley that is continually giving out new material, right? Erupting new material and separating or moving away this particular plates that you have right here. All right, so it moves or it enables these two plates to move away from each other. So as it provides this new material from the mantle. Okay, so this is now the South America and this is now the Africa. So this is how the Atlantic Ocean was born. All right. Now, if we look at the thermal images that we have right here, so the red one means this is the hotter portion, and the blue one is the colder portion of the oceanic crust. Alright, so as you can see here, the red ones are mostly seen on the ridges. So it means that a new material is being brought out in this particular region, and as it does, it moves away from the center. Then when it moves away from the center, it cools down eventually. And in terms of age, between the one located far away from the center of the ridge, okay, so this is much older The one over here is much older than the one located at the ridges of your divergent plate, okay, or divergent boundary. All right, so that is the age of the oceanic crust. So take note again, the one that is located at the ridge is much younger than the one located far away from the ridge. Okay, so that is the age of the oceanic crust. Right now, example of this place where we can find this plate movements is the country Iceland. All right, in this country, the country is divided into two parts. We have the North American plate, and on this side, we have the Eurasian plate. Now, these two plates are divided by the one that runs at the middle of it, which is called the Mid-Atlantic Ridge. All right, so this is okay. This portion of the Mid-Atlantic Ridge is somehow very active in as we speak right now, and it contains a lot of active volcanoes. Right? It contains a lot of active volcanoes, and it separates, right? It separates and it dumps new material on this country, on this particular portion of this country, and the two plates that you have right here is moving away from each other as it does, as it dumps new material coming from the mantle. Okay. Right, so the Mid-Atlantic Ridge is an example of a divergent plate boundary. All right, let's try to look for more places where we can find divergent plate boundaries. All right, so this is on Iceland. So as you can see here, the land was separated, right? The land was separated due to the movement of the lithospheric plate away from each other. Right, so that is the view from below, okay, below or underwater. Yeah. Okay, next one, this is what the oceanic ridges looks like. All right, so the one at the bottom, the one over here is the new materials that are being brought out to the earth. All right, that are being brought out to the earth as it moves away from each other. Yeah, so these two plates are moving away from each other. All right, so next one. All right, so another example of a divergent plate boundary is the East Pacific Rise, which is located at the southern part, right? So southern part of your Mexico, and this East Pacific Rise is extending towards the Pacific Ocean down to the the part of the Mexico over here, right? The Baja California over there, yeah. So this is an example of a divergent plate boundary. All right, so not all divergent plate boundaries are seen underwater. All right, there are some plate boundaries that there are some divergent plate boundaries that are seen in continental plates. All right, example of that is the East African Rift Valley. All right, so this East African Rift Valley that we have right here is continually splitting the Africa. Okay, the Africa as you speak. So as it continues to move away from each other, a new material is being dumped at this portion of the Rift Valley. All right. When we said new material, this is a magma or this is a lava, all right, that goes out from an active volcano located at the middle of this rift valley that you have right here. So it will take million years before this rift valley to be completely separated from each other and allow the water from this Red Sea, all right, to pass or to go over this gap that you have right here. So as of now, it is the Rift Valley continues to move away from each other. All right, so that is the East African Rift Valley. Now, if you want to know more about the East African Rift Valley, there's a link in the description or up there. All right, so there's a link up there. You can click that one and then try to or watch the details regarding about the East African Rift Valley. Right. So from outer space, it looks like somewhat like the one that you have right here. So this is the African Rift Valley over here. Now, over a million years, it will separate. All right, it will separate and allow the water from the Red Sea to pass through it. All right. So that will be the effect if the East African Rift Valley continues to separate time and time again. All right. Okay, so this is the East African Rift Valley in different view. Okay, right. So the Red Sea also is an example of a divergent plate boundary. All right. So the Red Sea was born out of the separation between the African plate and then the Arabian plate over here on this side. Okay, so that's how the Red Sea was born. Okay, water from the Indian Ocean, okay, rushes as the two plates separate millions of years ago, and then it forms this majestic Red Sea that you have right here. Okay. All right. So that was the divergent plate boundary. All right, or the constructive. We called it the constructive margins. All right. So next one. Alright, so next one that we have right here is the convergent plate boundaries. So what are these convergent plate boundaries? Convergent plate boundaries are plate boundaries that allows the plates to move towards each other. Alright, as it moves towards each other, it creates different scenarios. Alright, so we have right here three styles of convergent plate boundary. We have three styles of convergent plate boundary. So we have one that is continent to continent collision. Then the other one is Continent-Oceanic Crust collision. And the third one is the ocean to ocean collision. Alright, so these three types of collisions that you have right here that are under the convergent boundary creates different geologic structures. All right, so let's try to find out what are those geologic structures. All right, so first one, you need to take note that when there is a convergent plate boundary, there is always, okay, there are parts of it which is called the subduction zone. All right, there is a movement called subduction. This is where, all right, this is where a denser plate sinks below the less denser plate. All right, so we know it already from our first module that the continental crust is less dense than the oceanic crust. So typically, oceanic crust is the one that sinks below the continental crust, and when it does, it do a motion called subduction. All right, so in the subduction zones, there are a lot of weird things that is happening. All right, so there are parts of the lithosphere that are melted down. All right, and it creates this volcano that you have right there. All right, that you have right there on this picture that you have over here. All right, so let's try to find out where is this subduction zones can be found, and what effect it does when you have a subduction zone in a typical convergent plate boundary. All right, let's start first with the continent to continent collision. All right, so but before we go to this one, let's let's try to look first at the simulation that I have right here coming from the PET. All right, coming from PET. All right, so let's see that one. All right, so over here is the simulation that showcase the plate motion. Okay, so earlier, we discussed what is on the divergent plate. Alright, so we discussed the divergent plate boundary, and this simulation is very good in representing, alright, it will help you understand how the divergent plate works, alright, by just clicking things that we have right here. Alright, for example, we have here a continental crust. Okay, so for example, we have here a continental crust over there. Okay, and we put another continental crust over here. Alright, so if you want to do it in automatic mode, you may want to, or you can do it in a manual mode. Alright, so by the way, there's a link in the description below this video where you can download this particular simulation, and don't forget to donate to them. Yan, it will help this company a lot in providing us a simulation like the one that we have right here. All right, so let's have the automatic mode. So in this case, so we have here the continental crust. So since we discussed first the divergent boundary, so so the movement of the divergent boundary is moving away from each other. The two plates are moving away from each other, and this is how it does. All right, so when we play it, right, so you can put it slower. Okay, so as you can see here, okay, so as you can see here, if we were going to reset it again, okay, and in an automatic mode, so in a divergent plate boundary, so as you can see, there are no, right, all right, so there are no gaps in your plates that you have right here. Now, as it moves, as the new material from the mantle is being dumped on the Earth's surface, it creates this gap at the center. Okay, it creates this gap at the center that separates the two plates from each other. Okay, so when it does, all right, so when it does, right, the gap between the two plates widens, and in terms of age, all right, so in terms of age, younger materials are located at the center, all right, located at the spreading ridge that you have right here, or the rift that you have right here, and the one that is on the side is older than the one at the center. All right, so typically this is a rift valley. All right, when two continental plates, take note, when two continental plates separate, like the one that you have right here, it forms what they call the rift valley. Right, it forms the rift valley. All right, so the one underneath the ocean, all right, underwater. Okay, so let's reset this one again, and it. There you have it. All right, so let's have a two oceanic crust over here, and let's put again the temperature, right, for us to see. Okay. Now, in a divergent boundary underwater, it will form what they call spread ridges. All right, it will form ridges. All right, so in this case, take note of that. A divergent plate boundary that is underwater is called ridges. All right, so okay, so as new material is being brought here at the center of the ridge, it creates this gap at the center. All right, it creates this gap at the center where the plates on both sides are pushed away from each other. All right, so this thing happens around several million years. All right, several million years before the two plates are being separated. All right, so as you can see here, new materials are found at the center. Right, new materials are found at the center, while okay, older materials are found on the side of the ridge that you have right here. All right, so that is the divergent plate boundaries. All right, so let's go back to our 8. All right, so we are done with the divergent. So we have here the continent-to-continent collision. All right, so this is the first type, or this is the first style of convergent type boundary. All right, the continent and continent collision. So as you can see here, when two continental crust, which is both less dense, collides with each other, right? Some of them will subduct, all right? But most of the time they will go, all right? The force of the impact will allow the two crusts to move upward. All right, to move upward. So as you can see here, as it moves upward, it forms these mountain ranges that you have right here. All right, from a simple flatland over here, as the two continental crust collides, it forms, or the crust itself is moved upward, and it forms this mountain range at the middle. All right. So if you are if you are asking why there is why there is something that is subducting on this place, because probably before the continental crust there is an oceanic crust. There's a portion of an oceanic crust that collides with this continental crust. So as we all know, oceanic crust is denser than the continental crust, so that is why it subducts. All right. So when there is no more oceanic crust left, the continental crust will not subduct in the process. Therefore, there is one direction that it will go. It will go upward. All right. So it will form these mountain ranges over here. So okay, this is the story where the India. All right, the India is a separate continent, just like Australia. All right, long time ago, and as it converges with the Eurasian plate, the one that you have over here, as it converges with the Eurasian plate, as time passes by, it approaches the Eurasian plate. Okay, as the picture is showing to you, it approaches the Eurasian plate as time passes by, and after 10 million years ago, all right, 10 million years ago, it collided with the Eurasian plate, the one that you have over here, and formed these majestic mountain ranges that we know. And that is the Himalayan mountain ranges. All right, so this is how this mountain ranges was formed. All right, so mountain ranges was formed when two continental crust collides. All right, so you have here extensive folding. All right, you have here extensive folding of the lithosphere, thus forming the mountains that you have right here. Very good example that you have right here. The tallest peak that you have right here is the Mount Everest. All right, that is part of the Himalayan mountain range. All right, so as we speak right now, the India is continually pushing to the Eurasian plate. All right, they are continually colliding, thus making this mountain range go up higher. All right, it makes this mountain ranges over here goes up higher. All right, so that is the continent to continent collision. All right, so but before I show you the simulation about this one. All right, now remember that in the divergent boundary, all right, new material is being added through the Earth's surface. Now, my question to you, you can put this one in the description, in the comment section below this video. Think of this question. Now, if new material is being added to Earth's surface in a spreading ridge or in a rift valley, why does the Earth doesn't increase in size? Right? So that's the question. If new material is continually to be added in the rift valley and in the spreading ridges, in the divergent plate boundary, why does the Earth doesn't get any bigger at all? All right, or any larger at all? All right, so you put down your answer down the comments section below this video. So let's take a look at the simulation between continent to continent collision. All right, so here we are again in the simulation. So this time, we are done with the divergent. So let's take a look. New crust again. Okay, so when two continental crusts collide, all right, so when two continental crusts collide, so it looks like this. So as you can see, in terms of density, all right, this is both less dense, all right. So what will happen if both crust, which is if both lithosphere, which is if both crust rather is less dense, collide with each other? So this is what it looks like. So as you can see, right, there is a lot of compression happening at the center. All right, there are a lot of compression that is happening on the center. All right, so there's a lot of compression. So as you can see, there are now an impression of, right? There are now impression of a mountain range formed at the center when the collision happens. Alright, because the two continental crusts, alright, there are no way, okay, there's no other direction where the continental crust will move, rather going upward. So as you can see here, alright, as you can see here, it forms now the, alright, so it forms now the mountain ranges that we know earlier, which is called the Himalayan mountain range, when the two continental crusts collide. So probably this is the Eurasian plate and this is the Indian plate. When they collide, alright, they form this mountain range at the middle. Alright, so that is the continent-to-continent collision. And take note, when these two continental crusts collide, it forms mountain ranges. Alright, so let's go back to our slide. Okay, so that is the Himalayan mountain range. Alright, so the Alpine mountain range is also a product of continent-to-continent collision. Alright, so when Eurasian plate, alright, collides with African plate, the one at the bottom of this video, of this picture, the African plate, as we speak now, it continues to collide with the Eurasian plate over here. Alright, and forming this Alpine mountain range that you have right here. So probably in the future, several million years to come, the Mediterranean Sea will be closed out due to this collision that is happening. Alright, so next one. That is the Alpine mountain ranges. Right, so that is located in Switzerland. Okay. Alright, so the next one, the next style of continent-to-continent collision is called the Continent-Oceanic Crust collision. Alright, this is much more complicated than the first one, which is the continent-to-continent, because there is a geologic structure that is formed here. Alright, there are several mountain ranges, plus there is a volcano. Alright, not only that, there is also what they call a subduction zone. Right, the one that you have right here. Because a denser plate will now collide to a less dense plate that you have right here. Now, what it does is the oceanic crust is diving below the continental crust. Now, as it does, there is a friction that is happening over here. Right? There's a friction that is happening over here, and this friction will create this magma chamber. Right, will create this magma chamber and supplies this. Okay, as we all know, when a material is heated, it becomes less dense. So this material over here will float above. All right, will float above and then will be deposited in this magma chamber over here that will power up, or that will power up these volcanoes that you have on the Earth's surface. Right, so that is the continent-to-oceanic crust collision. So let's take a look at it in the simulation. Right, so let's go back again to the simulation and simulate. Alright, we will going to simulate the continent-to-oceanic crust collision. Alright, so okay, new crust, and let's put the continental crust on this side, and let's put the oceanic crust on this side. So as we all know that oceanic crust is less dense than the continental crust. Alright, so okay, so let's put the density over here and let's see what will happen if those two collide. So as you can see, there's one over here that is subducting and forming some sort of a trench over here. Right? It is forming a trench over here. And aside from that, okay, we'll take a look at the temperature on this portion. Alright, so let's take a look at. So as you can see, the materials over here. Alright, let's take a look at the temperature of the materials here. Okay, so this is higher. So it tells us that it is continually heated, so it becomes less dense. So as it becomes less dense, it goes upward. This materials goes upward and it powers up. It supplies the volcano with lava. Alright? It supplies the volcano with magma, rather, and this chain of volcanoes over here is the product of the subducting part of the oceanic crust doing okay, so these volcanoes that you have right here is a product of the collision between continental crust and the oceanic crust, respectively. Now, as you can see, this material is somehow heated, and compared to the temperature of the continental crust, it is different. Alright, so there is a friction happening over here. That is why the material is being heated and it moves upward and supplying the magma chamber with magma, and eventually it will become a lava when it goes out of your volcano. So this is what it does, alright, in a continent to oceanic crust collision. Now, what are these geologic structures that we have right here? Okay, so these geologic structures that we have right here are called the continental volcanic arc. Alright, so we called it the continental volcanic arc. So what do we mean by continental volcanic arc? So as you can see, these volcanoes are placed in a continental crust. That is why it is called continental. So why is it volcanic arc? Because there is a chain of volcanoes, alright, on this particular side of your continent. That is why it is called volcanic arc. Volcanic arc means chain. Right? Volcanic arc means chain. It means chain of volcanoes located at the continental side of the plate boundary. Alright, so that is the continental volcanic arc. Alright, so take note, when continent and oceanic crust collide, it forms the continental volcanic arc. Okay, let's go back to our slide. Alright, so that is the continent to oceanic crust collision. Alright, example of those where we can find this continent-oceanic crust collision, the Cascades. Alright, so the Cascades are very good examples of continent-oceanic crust collision. So these mountains that you have right here, and it has a volcano. A typical volcano that you will see here is the Mount St. Helens, the one that you have right here. Right, a very famous volcano. Alright, so Mount St. Helens and other volcanoes that you have right here. Right. It is forming together with the mountain ranges over here. Okay, so that's the Cascade that is located in the Pacific Ocean and the western part. Alright, so the western part of your United States. Right, so that is the Cascades. Alright, next, the mountain ranges located at the southern tip of South America in the in the country called Chile. Alright, so South American continent is colliding with the Nazca Plate over here. Alright, in the Pacific Ocean, and it forms these Andes mountain ranges that you have right here, and it has some volcanoes on it. Alright, so this is what they call your continental volcanic arc. Alright, so same thing that you have right here. This is the continental volcanic arc. Right. So, okay. So that is the continent to oceanic crust collision. Alright, so the next one is the ocean to ocean, or the last style of continent to continent collision is the convergent boundary is the oceanic to oceanic plate collision. Alright, so in this kind of collision, there is a subduction zone. Alright, so in the simulation that we will have later, we will try to find out what will happen if two denser plates, alright, if two denser crusts collide with each other. Alright, so let's take a look at the simulation. Okay, again, we are here on this simulation. So, new crust, and let's try putting an old oceanic crust over here and an old oceanic crust over there. Alright, so as you can see, both of them are denser. Alright. Okay, so both of them are denser. So just to check out. So let's do the convergent plate boundary. Alright, so let's do the convergent. Alright, so unfortunately, there's no convergent here. So, okay, let's put this one. Alright, there you go. Okay, so let's put this thing in motion. So both of them are denser. Just to check out first. Alright, so both of them are denser. So what will happen if two denser crusts collides with each other? So as you can see, the other crust will sink at the bottom. This is now your subduction zone. Right? This is now your subduction zone. And as you can see, there is a continuous friction happening on this area. There's a continuous friction happening on this area, thus the temperature will increase there and allowing this material to float, all right, to become less dense and float upward. All right, so these new materials that you have right here will supply, all right, so will supply the volcanoes found on the Earth's surface that you have right here, right? So this is not anymore found in the continent. These volcanoes are found in the oceanic crust. All right. So when two oceanic crusts collide, it forms what they call the volcanic island arc. All right, volcanic island arc. All right. So what does it mean? So it forms an island of volcanoes. All right. It forms an island of volcanoes that is formed in a chain. All right. Remember, volcanic arc means chain and island means island. So these islands that you have right here is forming a chain of volcanoes respectively. As this particular part of the oceanic crust sinks, all right, sinks at the bottom of another oceanic crust. So as it does, it supplies a material coming from the subduction zone. Example of this is molten rocks. It supplies the volcanoes on this volcanic island arc. Therefore, it gives off some lava and creates these islands over here. All right. So this is the scenario where your oceanic crust and oceanic crust collides with each other. All right. So that is the plate collision that you have over there. All right. Let's go back to our slides. Okay. Okay, so again, before you might forget this one, when two oceanic crusts collide, it forms a volcanic island arc. All right, and not only that, there's also a trench. All right, there's also a trench which is much deeper than the one that the one I featured earlier. All right, so the deepest trench are found where the two oceanic crusts collide, which is called the Marianas Trench. All right, the Marianas Trench is located where the Pacific Plate collides with the Philippine Plate. All right, so that is the Marianas Trench. Okay. Okay, so as I shown earlier, yeah, on the simulation, so these are the volcanic island arc, and this is the trench that I am talking about. Okay. All right, so example of this where we can find the two oceanic crusts colliding with each other. So number one is on the Alaskan island regions, which is called the Aleutian Island. The Aleutian Island is product of the North American plate colliding with the Pacific plate at the bottom. All right, so this is the Pacific plate, and this is the North American plate. So when it does, all right, it forms this volcanic island arc on your Pacific Ocean. All right, so there you have it. Okay, next one. Okay. Next is the Marianas Trench. So this is the Philippine Plate and this is the Pacific Plate. So as we all know, the Marianas Trench is the deepest trench, all right? The deepest point in this planet. So that's it. Okay, next. Okay. So there is also a trench, all right? So the Caribbean Plate, when it collides with the North American Plate, there's a trench, all right, in between that. And the island that it forms there, the Caribbean islands, the Cuba, the Bahamas, the Puerto Rico, something like that, is being formed when these two plates collide with each other. Alright, Philippine Islands. Alright, Philippine Islands is formed by oceanic to oceanic crust collision. Alright, so Indonesia as well, and also Japan is formed by that style of collision. Okay. Alright, so we go now to the third and last plate boundary, which is called the transform boundary. So as you can see here, alright, so this is somehow, alright, if the convergent boundary is the, alright, so if the convergent boundary is the destructive, alright, so it is the destructive, it's also called as the destructive margin. Alright, transform boundary, alright, is a boundary where the plates doesn't move away from each other, alright, doesn't move towards each other. Instead, the plates are sliding past each other, alright. The plates over here are sliding past each other. So, most of the time, transform boundaries or transform plate boundaries can be seen, alright, can be seen on places where there are two or more, alright, where there are two or more plate boundaries interacting with each other. For example, when you have two divergent plate, alright, when you have a two divergent plate boundary, something in between them, there is a transform plate boundary. When there is a two convergent plate boundary, in between them, alright, in between them is a transform plate boundary. Alright, so as you can see here, alright, so as you can see here, the two plates are being grinded, alright, being grinded as they slide past each other. Alright, so very good example that you have right here is the San Andreas Fault. Okay, so this is the San Andreas Fault viewed from above. Okay? So this is the only, alright, so this is the only transform plate boundary that can be seen on the Earth's surface. Most of them are found underwater. Alright, so most of them are found underwater. So that is why we can appreciate it. So here we are here. I have right here is the San Andreas Fault. This is the place where you can find the transform plate boundary working. Working as it should be. Okay, so let's go back again to the simulation one more time to view what is a transform plate boundary all about. Okay, so in a transform plate boundary, okay, so let's have a new crust and let's put there. Okay, so there are two scenarios. There are two scenarios here. There are transform plate boundary in a continental crust. Alright, and there are also transform plate boundary in a oceanic crust. In an oceanic crust. So, let's start first with the continental crust. So, okay. So, the one that you have right here in a transform plate boundary, there you go. So, let's put it in a slow mode. Okay, so as you can see here, the two continental crusts slide past each other. So, as it does, there's a portion of a plate at the middle. Alright, at the middle of this simulation, there's a portion here of the plate that are being destroyed as they grind past each other. Alright, so as you can see here, the movement is parallel from each other. The two plates are moving parallel towards each other, or parallel away from each other. Alright, so that is, okay, this is the continental, this is the transform boundaries at the continental crust. Now, what does it look like in the oceanic crust? Okay. You have it. Okay, let's have the transform. And this is how it looks like. Okay, the same way with the continental crust. Alright, so the same way. So, although we can see it right here, there are a lot of materials, there are a lot of rocks that are being grinded over here. Alright, as the two plates, alright, as the two plates over here slide past each other. Okay, so there are no materials, there are no new materials that are brought upward. Alright, there are no materials that are being destroyed, right, in this particular plate boundary. That is why it is called conservative plate margins. Alright, transform plate boundary is also known as the conservative because there are no plates that are being subducted. There are no materials that being added on the Earth's lithosphere. So that is why it is called conservative plate margin. Alright, so that is the transform plate boundary. Let's go back to our slide. Okay, so There you have it, the transform plate boundary. So where where we can find this one on the continental crust, and the other one is underwater, or the oceanic crust. All right. So go. Okay. So this is the tectonic plates, all right, that divides the Earth's surface that we have that we all know. And as you can see here, there are some that are there are some that has a subduction zone. All right, so meaning to say that the plates over here are colliding with each other if there's a subduction zone. All right, over here also has a subduction zone. Okay, all right. So the heavier line, the one that you have right here, this one over here, means that there is a plate that is diverging. Right? There's a plate that there's a plate that is diverging on this particular portion of this plate boundary. Now, at the middle of it, all right, there's another divergent plate over here. Now, at the middle of it, there is a thin line. All right, there's a thin line. Okay, over there, and that thin line represents the transform plate boundary. All right, so meaning to say, this area, the plates there are sliding past each other. Right, so there you go. Okay. All right, so okay, this is the connection between the plate boundaries, the volcanoes, the earthquake, and the mountain ranges. All right, these are the connection between the three. Okay, so the mountains, the earthquake, and then the volcanoes. This is the connection of those three between the connection of these three on the plate boundaries. So what is the connection between them? All right. So as you take a look at this map, all right. So as you look at this map, where are the volcanoes placed aside from this one? Right? Aside from this one. This is a hotspot volcano and has nothing to do with plate boundaries. All right. So as you can see here, all volcanoes are formed in the plate boundaries. So meaning to say that the volcanoes have a definite relationship, or they are very related with plate tectonics. All right? They are very related with plate tectonics. All right? So okay, volcanoes are somehow located at these points where the plates are colliding. Okay, to be exact. Okay. So, volcano. All right, so volcanoes are formed by the following things. So, number one is subduction. Number two is by rifting when it happens on the continental crust. And number two is by hotspot. All right, so hotspots. All right, so that is where the volcanoes are formed. All right, not only on the continental crust but also under the oceanic crust. All right, okay, so there's also a volcano right there. All right, so next one. All right, so where do earthquakes form? All right, so the earthquakes are formed definitely where there is a tectonic plate. Okay, so as you can see here, when there's a subduction zone, there's an earthquake. When there is a transform fault, there is an earthquake. When there is a divergent boundary, there is an earthquake. So definitely earthquakes are very much related with the plate tectonics. All right, so or the tectonic plates to be exact. And also with the mountain ranges. So as you can see, mountain ranges are formed. All right, so as you can see, mountain ranges like the one that you have right here. All right, so let's have this one as an example. All right, even though this will become a volcano. All right, so as you can see, mountain ranges are formed when there is a plate colliding with each other. All right, example is the Indian plate and then the Eurasian plate, the African plate and then the Eurasian plate. All right, so on and then so forth. So that is the relationship, or meaning to say that the mountain ranges are also related with the tectonic plates. So therefore, mountain ranges, earthquakes, and volcanoes are related to tectonic plates. Right? So there's no doubt about it. Right. So as you can see here, so these are the earthquake epicenters. All right. These are the earthquake locations happened for the past 10 years. All right. That was 10 years ago. All right. So as you can see, it gives us an impression that it looks like a plate boundary. All right. It gives us an impression that it looks like a plate boundary. So because earthquakes happen where there are plate boundaries. So there's no there's no doubt that these earthquakes look like the shape of the plate boundaries that I have taught you on the first module. Right? So there you have it. Okay? Some of them have varying intensity, some of them are large, some of them are have very small intensities, all right? So those are the earthquakes. All right, so to sum it up, all right, to sum up everything that we have learned this morning, all right, so this is the table. So we have here the divergent plate boundary. So it can happen on the ocean, and it can happen also between two continental crust, all right? And we have the convergent plate boundaries. There are three places where you can find convergent plate boundaries. We have ocean to continent, ocean to ocean, continent to continent. And we have the last one, which is called the transform plate boundary. So as you can see here, all right, so as you can see here, the plate movement is apart when there is a divergent. The movement is together when there is a convergent. And the movement is sliding past each other when the plate boundaries are transformed. All right, are transformed plate boundary. So these are some examples or the locations where you can find these plate boundaries that we have discussed earlier. Okay? So these are the events, all right, that you can that you can take note of, all right, when there is a divergent plate boundary that is on that area, and also with the convergent ones. Okay. All right. So, what will happen in the future? All right, what will happen in the future? All right. So, as it continues to move, the plates that we have right now, the plates that we have discussed a while ago, okay, they are not stationary. They continue to move as we speak. So, example, the Pacific plate is moving northwest at 8 centimeter per year. The North American plate is moving west at 2 cm per year. And the Indian plate is moving northeast to 12 cm per year. So, as you can see here, after 200 million years, the Atlantic Ocean will be the largest ocean in this planet, not anymore the Pacific Ocean. All right, the Pacific Ocean is being compressed as the North American plate move westward. All right, so this will be the net result. And after 50 million years from now, Africa will move north. It will close the Mediterranean Sea, right? That we all know. So as you can see, the Mediterranean Sea is very large. It will be closed out as these continents or as these plates move. The African plate is moving north to the Eurasian plate. All right, the East Africa will be detached, all right, respectively, as we discussed earlier. And the California will be traveling northwest, and it will be swallowed, all right, 60 million years from now in the Aleutian Trench. So California region, the regions in the California will be on the ocean floor or will be at the bottom of the ocean up 6 million years from now. All right, so Atlantic Ocean will grow, the Pacific Ocean will sink respectively. Right. So with that, okay. All right, to summarize everything, so on the surface of the Earth, there are tectonic plates that are moving around the globe, and these plates are made up of crust and then upper mantle, which we call the lithosphere. And there are three types of plate boundaries as these plates move, okay, move around the move on the Earth. So we have the divergent, we have the convergent, and we have the transform plate boundary. Volcanoes, earthquakes, and mountain ranges are closely related to tectonic plates. Alright, so with that, I end up this video with a quote from the man himself, Alfred Wegener, who proposed the continental drift theory. We are like a judge confronted by a defendant who declines to answer, and we must determine the truth from the circumstantial evidence. This is the time where Alfred Wegener has been vindicated, all right, has been vindicated or ostracized because of his idea about how the continents um, were in the past, all right, because of his idea about these continents. Okay, so time and time again, his ideas about this continental drift theory are being supported by some evidences coming from our geologists and scientists, all right, of alike. That makes this person that gives this person a well deserved, all right, a well deserved salute, all right, over his continental drift theory. All right. So with that, that ends up our video lesson this morning. So if you have learned something from this video, you can give a thumbs up on this video. All right, and you can hit the notification bell and subscribe on this video if you want to be updated by more with more of these videos to come in the future. All right, so if you are not satisfied with this video, you can put some comments at the comments below in this video. That will help me a lot in improving the videos that I will create in the future. So if you do have questions, also put your questions in the comment section below. All right, so that ends up our video lesson today. Okay, that ends up our video lesson today, and let's see each other on the next video lesson. All right, so that's it. Bye, everyone.